So, welcome to the sixth experiment that we are going to demonstrate today. And in the previous experiment, you have done the estimation of iron 2 plus using potassium permanganate. Today, we will discuss about potassium dichromate titration using BDS as the indicator. One minute. Is it possible to hide this? Anyway, let it go there. And this one go there. Okay. So, as you know, the reaction that we are doing is the oxidation reaction of Fe2 plus to Fe3 plus, and in this particular experiment we will do it using dichromate 2 minus getting reduced to chromium 3 plus water. So, when we try to do the balancing of this reaction, add and balance, you will see something. So, if you try to first balance it, you need 7 water molecules to balance the oxygen that is there in dichromate, and 7 water essentially means 14 H plus to be added on this side, right. Now, you see the charge is also balanced on both sides, right. This is Fe3 plus, sorry, 1 minute. This side is 2 plus and the other side is 3 plus. So, now what we again see is that this reaction requires sufficient amount of acid. So, as we have done in case of oxalic acid permanganate solution or permanganate iron estimation, we added a certain amount of acid before the titration. Here also we need to add acid, and what acid should we add? We should add dilute sulfuric acid, not nitric acid or HCl. Of course, HCl will not cause any harm here, because I think in the previous class wrote about it. E0 value for Cr2O7 2 minus to chromium 3 plus is about 1.31 volt. E0 value for Fe3 plus to Fe2 plus is 0.71 volt, and E0 value for chlorine to chloride is 1.36 volt. So, this is higher than that. So, dichromate cannot oxidize chloride to chlorine, but it can oxidize iron to iron 3 plus. But you see, dichromate is a bright orange colored solution. Iron 3 plus is faint yellow in water, and this is green, pale green. But then, as soon as you start adding dichromate, the solution which was initially iron 2 plus was nearly colorless, will start showing some color because of these two cations. And at the end point, this orange color will not be visible on top of these two colors which got intensified during the reaction, because as the reaction proceeds, more and more amount of chromium is formed and the color becomes more and more greenish, and this faint yellow color is already hidden below that greenish color, and this orange color cannot be seen at the end point. So, in this particular titration, we would need an indicator which will indicate the end point of the reaction. So, now we need to decide on the indicator what kind of indicator it should be. It should be a redox active indicator. So, I should have an indicator whose oxidized state to the reduced state E0 value should be less than 1.31, but should be greater than 0.71 volt, right? This value is for Cr2O7 2 minus to Cr3 plus, and this value is for Fe3 plus to Fe2 plus. So, the indicator should have the E0 value between these two numbers. Why not smaller than that? What will happen if we take an indicator where it's yes, so that will be not oxidized. Fe no, if the indicator E0 value is suppose 0.65 volt, what will happen? Fe3 plus will get converted to Fe2 plus, and indicator in the reduced form to get oxidized to its oxidized form. That is one problem. But if you don't have iron 3 plus in solution, suppose when you are starting the experiment, you don't have any iron 3 plus, you only have iron 2 plus. So, in that, if you add the indicator, it will have its own color, right? If you add the reduced form of the indicator, it will have its own color. Now, what will happen is, if you add a drop of dichromate to a solution where the indicator has E0 value like this, dichromate will first oxidize the indicator and change the color before oxidizing iron 2 plus to 3 plus. So, your purpose will not be served. So, that is why we need to choose some indicator whose E0 value falls in this range. The E0 value is greater than 0.71 but less than 1.31 volt. So, there are two different indicators that are used. One is a simple diphenylamine, which is very easily available and is not very expensive also. This diphenylamine, when you add Cr2O7 2 minus, it first undergoes irreversible dimerization reaction like this. This dimerization reaction is irreversible. So, this dimerized compound then reversibly gets converted to a species which is this one, which is technically a resonance structure of the dimer compound. Resonance, or you may say that hyperconjugative structure. Right? And this structure, this compound is deep violet in color. So, if we take diphenylamine as the indicator, which has the corresponding E0, E0 for indicator ox to indicator red value equal to 0.78 volt. Then this reaction can be used to identify the endpoint of the estimation of iron. So, when you start the reaction, you have only Fe2 plus. Then you add Cr2O7. Okay, let us take it as Fe2 plus plus indicator in its reduced form. This is the reduced form, and this is the oxidized form. So, this will first oxidize all iron 2 plus to 3 plus till everything is oxidized. The indicator will remain in its reduced state. After completion of oxidation of iron 2 plus to 3 plus, any excess Cr2O7 2 minus, that is, you add one extra drop of dichromate, this indicator will then get oxidized to its colored oxidized form. As a result, you will see a drastic color change. This diphenylamine that you have is colorless, whereas this is dark violet in color. Now, the problem is that this diphenylamine is not soluble in water. Why? It is like aniline, right? Aniline does not dissolve in water. Very little amount of aniline dissolves in water. Now you have removed one hydrogen of aniline and replaced it with phenyl. So, it has become diphenylamine. It is further less soluble in water. So, to solubilize this, one has to use concentrated sulfuric acid to form a salt of diphenylamine and then dissolve in water. Instead of diphenylamine, we use barium diphenylamine sulfonate, which is this one. This is a sulfonic acid salt of diphenylamine. So, we had a diphenylamine sulfonic acid and the proton is removed and barium is added as a counter ion, barium 2 plus. So, this is a colorless solution, colorless compound, and this being ionic compound, it dissolves nicely in water. Aqueous solution of barium diphenylamine sulfonate works as a very good indicator in this particular redox reaction, which is also done in your in aqueous medium. So, when we I have got the video, you will see the video. I have tried to demonstrate the appearance of different colors using a different camera and then put it as inset in your main video. So, you will see that slowly when you add dichromate to a solution of iron 2 plus, the color of the solution turns greenish. it becomes darker green towards the end point, but then just at the end point, when we add one extra drop of potassium dichromate, the color immediately changes to violet, indicating the end point has been reached. So, for your calculation purpose, I am giving you the strength of potassium dichromate. So, the laboratory assistants made the standard solution using these amounts of dichromate. So, I am giving you the weight of weighing bottle plus K2Cr2O7 before transfer as 31.3187 gram, weight of weighing bottle plus dichromate after transfer of certain amount of dichromate as 30.3187 gram, and this amount of dichromate was transferred to 250 ml volumetric flask and was dissolved in water and diluted up to the mark. So, calculate the strength of this in normality. What was the strength of this in normality? How will you do that? What is the equivalent weight of dichromate? How do you calculate the equivalent weight of potassium dichromate? Molecular weight by how many? So what is divided by 5 or 6 or 3? Yes, divided by 6. Yes. There are 2 chromiums. So, there are 2 chromiums. Each chromium is transferred to by 3 units. So, dichromate to chromium 3 plus is a 6 electron transfer. So, molecular weight divided by 6 is the equivalent of weight of dichromate. And you know this x gram of dichromate has been taken and dissolved in water and diluted to 250 ml. So, you should be able to calculate what is the strength of this dichromate solution that they provided. With that dichromate solution, we have standard estimated the concentration of iron 2 plus in the supplied solution. So, in the procedure you will see that we have taken 10 ml Fe2 plus solution. To that we have added 10 ml 4 normal H2SO4. Eventually it becomes 20 ml. So, it is 2 normal with respect to H2SO4. But mind you, once again, this is the amount of iron you have taken. So, if when you are applying V1S1 is equal to V2S2, volume of iron is this. S2 is what you are going to determine. V2 is your burette reading and S2 is your concentration of dichromate that you will find out from this calculation. What is the amount of dichromate taken, where was it dissolved, and what is its equivalent weight. You can do that, right? Yeah. That means the solution has the acid strength as 2 normal. It is a dilute sulfuric acid solution. This is what we try to mean here. It is not a concentrated solution. We added 4 normal 10 ml sulfuric acid to a 10 ml solution of iron. So, overall volume of that solution is 20 ml. So, the strength of sulfuric acid there is just 2 normal. Concentrated sulfuric acid is 36 normal. 1:1 sulfuric acid is 18 normal. Those are really concentrated solutions. 4 normal sulfuric acid is also significantly concentrated solution. Then you dilute it to 2 normal. When you do any laboratory experiment, the qualitative analysis which you actually have not done in the lab, we provide you with 1 normal sulfuric acid, 1 normal HCl, 1 normal nitric acid, something like that is provided in the rack for you to use. So, those are dilute, very dilute acids that we use in the lab for any practical purposes. Okay. So, any other question? Do you have any other question? Yeah. Yes. No, it oxidizes indicator after the oxidation of iron. If you remember the redox values here, the value for permanganate was 1.54, 1.51 volt, right? Chloride to chlorine is this, and then iron is that. So, what will happen is, it will first oxidize iron 2 plus to 3 plus. When the oxidation of iron 2 plus to 3 plus is over, it will oxidize that, and eventually this entire amount will be consumed by the potassium permanganate itself, and then it will show the faint pink color. But in case of dichromate, this value is already lower than that. So, dichromate cannot oxidize chloride to chlorine. Dichromate only can oxidize iron to iron 2 plus and then the indicator. Yeah. No, I will tell you. I will tell you 1 minute. MnO4 minus will get reduced to Mn2 plus 4 water molecules, which essentially means 8H plus. This E0 is plus 1.51 volt. So, permanganate, when you add to a solution which contains chloride, will immediately oxidize it to chlorine, because the E0 value for this oxidation is minus 1.36 volt. This is more negative, and Fe2 plus to Fe3 plus, the oxidation potential is minus 0.71 volt. So, when you add permanganate, it will first oxidize chloride to chlorine, which is more negative. When chloride to chlorine oxidation is over, then it will oxidize iron to iron 3 plus. So, overall Buret reading will be the sum of those two. In this case, when you are doing it as Cr2O7 2 minus going to Cr2 plus, this reduction, just a minute, chromium 3 plus, right? This E0 reduction potential, this is a reduction reaction, is 1.31 volt. The Fe2 plus to 3 plus, the oxidation potential is minus 0.71 volt, and indicator reduced form to oxidized form, the E0 value of that oxidation is minus 0.68 volt. So, this is more negative. So, dichromate will first oxidize all iron 2 plus to 3 plus. It will not oxidize that until and unless every iron is oxidized to 3 plus. Then this indicator oxidation will take place because it has a less negative oxidation potential. So, the endpoint will be shown when the indicator gets oxidized. In this scenario, this 2Cl minus to Cl2, the E0 oxidation value is minus 1.36 volt. So, dichromate cannot oxidize chloride to chlorine because this is higher. This negative value, this reduction, the oxidation potential is higher than its reduction potential. So, if you consider both as reduction potential, this is higher than that. So, even you have a chloride ion present in your solution, you do not need to add Zimmermann, Reinhardt or any other solution to suppress anything. You can directly use the BDS indicator for titration of dichromate, titration of iron 2 plus using dichromate. Okay. Any other question? Normally we don't use HCl, but here one can use HCl, yes. So, yeah. The way I have written it, it is the 1 minute. This is the reduction potential because I am writing it in the reaction I have written as a reduction reaction. This reaction I have written as oxidation. So, this is oxidation potential. This is reduction to reduce to oxidize. So, this is oxidation potential. This is oxidation potential. Okay. Higher reduction potential means that is a stronger oxidizing agent. It is strong reducing agent, right? Yeah. Yes. One minute. I made a mistake. Very good point to be noted. I made a mistake here. Let me correct the number. While writing, I wrote the same decimal place. Sorry, very good point. It is 0246. 0246. 30.0246. Okay. Mm. Yeah. It is more negative. It is more negative, and that is why it will get oxidized before the indicator gets off. Mm. Yes. No, no. In this particular case, dichromate cannot oxidize chloride to chlorine, because you are adding dichromate. You are not comparing with this. You are adding dichromate, which has a more tendency to get reduced compared to chlorine to chloride. So, this reduction takes place, and that cannot do this oxidation, because this oxidation potential goes higher. If you write it in the reduction terms, then it is plus 1.36 volt. The reduction potential of this, the reduction is plus 1.36 volt. So, when you try to compare, that is why I was always writing the reduction potential only, if you see here. So, this is a higher reduction potential than that, right? But this is a lower reduction potential than that. So, permanganate can oxidize chloride to chlorine, but not dichromate. Okay. So, while comparing the reduction and oxidation potential, it has to be compared either all in reduction mode or all in oxidation mode. Now, when I have this and that in solution, this cannot be oxidized, because the reduction potential, the oxidation potential is much more negative than that, whereas this and that can be oxidized. No, see, again, when you try to compare the values, you compare the values both in the reduction form. So, when you compare in the reduction potential, this has a higher reduction tendency than that. So, this oxidation will happen before than that. Actually, these two will happen all together, and then you will end up getting a combined result, not only one. Because what happens is, all these oxidation reduction potentials that we are writing are the standard reduction potentials, but then when you write down the Nernst equation, you will see the concentration or activity terms come up, and those activity terms continuously change and change their effective reduction potentials. So, when you use potassium permanganate in presence of chloride, iron you are trying to oxidize, you will see that from the beginning itself the smell of chlorine gas comes out, which means that chloride is getting oxidized to chlorine, and you know chlorine is not very highly soluble in water. So, when you add permanganate to a solution of chloride, immediately you will start getting smell of chlorine gas.